in mathematical finance. I hope you can all hear me and see me. We need to briefly start with a correction. So I prepared here some notes already. So first thing I like to point out, and it will be corrected in the lecture notes as well, is that there was a swap of capital T and little t here. So if you look at this, I mean, this is now the correct version. In the former version, this little t and the capital were swapped, and this is unfortunately a typo. You can't see this typo at the terminal time, but if you think about what the price of this constant k at time t is, you realize that yeah, the order has to be in this direction. All right, this is just, I mean, so please check the put call priority again to make sure that you have the right version of it in your notes. All right. And as usual, please just interrupt me if you have any questions. Okay, so let's come back to Martingales. So from now on, we always work on a filter probability space. So we consider a probability space F, P, and omega. And additional to this, we consider a sequence, family of sigma algebras, which are increasing. And this is what we call filtration. So what we want to consider, I mean, from now on, we always assume that we have as an underlying space a filter probability space. Right? And the idea of a filtration is that it allows us to model the information generated, for example, by some price process, or the information generated by a financial market. And then we introduced the notion of martingales, respectively sub and super martingales, which goes as follows. So we consider a real value process, X, which is indexed by under index set I, which is adapted to this filtration. And we assume that it's integral. Right? And then we call it a martingale if we have here this property of being a fair game. So the conditional expectation of X at time t, given the information at time s, is exactly the process at time s. So if you want to check that this something is a martingale, you actually need to check three properties, right? So first you need to check that it's has the right adaptiveness property. You need to check that it's integral at every point in time. And then you have to check that this is this fair game property is fulfilled as well, right? So I would like to emphasize this because it's a common mistake to miss one of these properties. So many people check just the third property, but this is not enough to ensure that something is a martingale. And then there are the notion as sub and super martingales, where you have martingale properties which are either in favor or not in favor for you, right? So depending on which perspective you take. So this was the definition we introduced last time, and then we started to discuss some examples. This is where I would like to continue today. So this is example 2.28. And we already did the first one, which were the random martingale walk. And now we want to consider the multiplicative version of it. So that's the second example. which is the multiplicative random or geometric random walk. So just to give you some more examples of a martingale, respectively sub and super martingale. So what we would like to consider here is a sequence of IID random variables y from 1 to n. So they are independent and identically distributed random variable. We want to assume that the expected value, so in particular the integrable of the e random variable is just equal to 1. Right. And well, this is for I when they're identically distributed, so this holds for all I. So as before, I mean, what we want to, in order to ensure that something is a martingale, we need to have a filtration as well. So we just take the filtration generated by this process of this sequence, y1 till yn. And well, to make it as usual, we assume that the zeroth filtration is just the trivial one. And now we define the process. So z is just given by the product of y1 up to yn. And again, just have as usually a process is starting from 0, we just set z0 to y0 equal to 1. So this is just a definition to extend our process to the time 0. Right. Now my claim is that this process z going from 0 to t is indeed a martingale. Right. How can we see this? I mean, we need to check it. So of course it's adapted because this is how we set up the filtration. And of course it's integrable because we assume that these random variables y1 to yn are independent and integrable itself. Right. So here we are fine by just checking this Martingale property that the conditional expectation of Zn given the filtration up to time m, so the filtration fm, and we want to show that this is equal to Zn, right? This is the defining property here 3 of a martingale. So what do we do? Well, we call the definition, so Zn is equal to Zm multiplied with respect multiplied with that ym up to time yn, right? And now this Zm is fm measurable, so if we take this conditional expectation, we can pull out the Zm, right? Because it's measurable. And now what we realize is, these ym up to yn are independent of the filtration fm because the random variables are independent. So this information of fm doesn't help us. So we just get here the expected value of ym to yn, or n. And here we are. Well, this is just 1. So by independence, so y are independent. we get Zn. Right? So indeed, we have seen that this is here now. Martingale. Okay. All right. Before we go on, let me give you another rather trivial example, which actually appears quite frequently. And this is what sometimes is referred to Levy's martingale. So how does it go? What we take, I mean, we can take a random variable x. It has to be integrable. And now we define the process, which is just the conditional expectation of x given information up to time t. Discrete time. But this process is obviously, by the definition of the conditional expectation, it's integrable and adapted. And by the power property, it is a martingale. Power property of the conditional expectation, right? All right. Okay, so this is just to keep, well, to have some examples in mind. And now we want to study properties of martingales, yeah, and also of semi and of sub and super martingales, but in particular of martingales. So let's come to lemma 2.29. Okay. So let us take two martingales, x and y. So taking our general index at eine. What did we do this here, right? Are martingales. Okay. Then the process a plus xt plus a multiplied, so a is a constant multiplied with the martingale x plus b times the martingale y is again a martingale for constants a, b. All right. So the class of martingales forms a linear vector space, right? You can multiply with the constant, so it's a real valued vector space. And you can add and multiply with constants. That's okay. Add two martingales and multiply with constants. If I have process x again, and we have assumed now that it's super martingale. This is the case if and only if x minus, let me make this red, so x, so minus the processor, that's really bad. So minus x is sub-martingale. So Right? If you have a game which is not in favor of you, so a super martingale, and now you swap all the signs by taking multiply with the number -1, well, this game is suddenly in favor of you because all your losses turn into gains and vice versa. All right. And another property we'll need later is, okay, let's assume X and Y are super martingales. Then the process Z, defined as the minimum of X and Y, is super martingale. Okay. And so this gives us an idea how we can transform it, transform it, which operation we can do for martingales and super martingales and super martingales, and how they preserve the Martingale property, or how do they change it. All right. So, I mean, the proofs are not really hard. So I leave this first one, so the linearity, this swapping here, as an exercise. I mean, it's nice to familiarize yourself with the definition of a martingale, but it's just checking left. Yes. Exercise. Right. Let me do, I mean, it's also not much harder. Let me check the last one. So I want to check if I have two super martingales, then the minimum. So the process generated by the minimum of F and Y is again a super martingale. So again, I mean, just to recall it for you, we have to check three properties. One is the adaptedness. Right, this is rather clear because you have a minimum of two adapted processes, so it's again adapted. So let's start with checking that it is integrable. Right. So what we want to check is that the absolute value of Z at time t integrated has a finite value. Well, so we want to estimate the minimum from above, which can be done by the sum. Right, so can estimate this by the sum of the absolute value of the integrals from X and Y. And this is finite by definition because X and Y are super martingale. Right? Since X and Y, so other way around, are super martingales. Okay, and now we need to check the super martingale property. So again, let's take an element in the index set I. And now we observe two things. So first, we want to estimate the conditional expectation of Z given the information of up to time S. Right? So we take two numbers, right? So S is more or equal than T. Well, we can always estimate the minimum with one term, so we can estimate this, and this is now the linearity of the monotonicity of the conditional expectation, and X is the super martingale, so we can estimate this with X. Right. And now we play the same game for the process y. So we estimate this by monotonicity with the y. And then we have the super Martingale property of. Right. So again, take here this and apply it here and here. Okay. All right. Okay. And now it's not. So if I apply these two inequalities and combine them, so I can estimate the conditional expectation of z at time t, given the information up to time s, by the minimum of x s and y s. Right. And this completes the proof. So we see that the z has to be a super Martingale as well. Okay. Okay. All right. Another transformation which appears, well, let's say frequently, so at least at several places, feature is that if we take, Martingale, so this is a Martingale, and we take a convex function, right? And these are, I mean, if you think of the payoff of call or put option, I mean, they are concave or convex. So, but if you know something for concave functions, convex functions, you also know something for convex function. We're just swapping the signs. So this is our statement. We take this as a convex function. Then we know if we take, we assume that the convex function phi applied to xt is integrable for all t and I, then the process given by applying this convex function to our Martingale X is submartingale. Okay. Again, proof is rather simple. So why is the proof simple? Well, the measurability, so the adaptiveness is directly transferred from the Martingale X. The integrability here is assumed as part of the statement. So we only need to check, again, the Martingale property. So let's take two elements here in the index set. It's usual s being less or equal than t. And now we observe that if we take the conditional expectation of x t and then applied the convex function to it, given the information of the filtration time s, well, we can use the Jensen's inequality to pull out the convex function. So we get here that the conditional expectation of x given f, and now this is a Martingale, so this is nothing else than conditional expectation is equal to the process at time s, right? Is Martingale. Right, that's it. This is, again, the property we need to check to ensure that it's a sub-Martingale. Okay. So first, so the simple properties which hold for general index set. And now I'd like to give you some decomposition of super and sub-Martingales, which translate them, these objects, to Martingales in a rather nice way. And this is given by Doob's decomposition. And I think this helps also a lot to understand super and sub-Martingales. So what I would like to do from now on is to focus really on the discrete time case. Focus on, because if we want to do the following results in a more general setting, well, I invite you to come to the Advanced Mathematical Finance course. So what I like to take now is my index set as our set we actually want to consider. So the set T, which were given by just the finite number of integers, right? So this. All right. One might think, if one restricts really to the discrete time case, is that we can really understand that the Martingale property is a local property, right? So if we consider a game over, like here, t time steps, well, it's a fair game if and only if it's a fair game in each individual time step. And this is actually the content of the next lemma is, well, process, why do I call it? Okay. X is Martingale if and only if the conditional expectation of xt given the information up to time t minus 1 is equal to xt minus 1 for all t in our index set t without 0, right? Because for 0, this is not well defined. Okay. You see, I mean, if you want to check the Martingale property in discrete time, it's really enough to check each time step, right? So you only check, given the information of time t minus 1, if you take the gains for the next round, which are given by xt, the conditional expectation has to be equal to xt minus 1. Okay. Yeah. Oh no, not proof yet. So I want to give you the similar statement for super and sub Martingales as well, right? They. So xt is sub. For super Martingale, if and only if, right, the I mean, the expected statements hold. So if you want to set a sub-martingale, the game is in favor. So your conditional expectation about the future, given the information at time t-1, goes up, and super if it goes down. And this has, again, to hold for all t in the index set t without 0. Okay. So now proof. And here I want to focus for the proof on the first statement. So I want to prove that something is a martingale if and only if it's locally a martingale. Okay. So that's what we're going to prove. And the one direction is, I would say, obvious. Just take the definition, right? So if I have a martingale, if I take the definition of a martingale, what does it tell us? Well, this property here has to hold for every s and every t in the index set. So obviously they have to hold for every time step, right? So that's easy. There's nothing to show. For the other direction, okay, we need to iterate a bit the argument. So let's assume we have here this local Martingale property and we want to show the global one. So let's take s and t from our index at t, and s n equal to t. Well, okay, this is, sorry, I mean, here's obviously something missing. Is it this good? Okay, there's a question, and I presume that life took over some account, so I ignore the question. But yes, I mean, I invite everyone to come to the Advanced Mathematical Finance course if you want to see the harder problems arising in continuous time. So what we wanted to assume, and I missed this here, so let me add it, because otherwise, of course, the statement is not 100% correct. Well, it's not correct. There's in mathematics no ambiguity is. So I want to assume that x t is adapted stochastic process with the expected value of the so it has to be integral for all t in t. Okay. And I need to correct this in the lecture notes as well. Okay. And then the proof, I mean, this lemma makes sense. So we only need to check here the Martingale property, which has to hold globally, and we assume that it holds locally. So let us consider the conditional expectation of xt given fs. Well, this is, or we can take a telescope sum and then we use the linearity. So this is equal to x at time s. And we actually want to show that it's equal to this, but this is our task. So we add here a telescope sum starting from S going to T. And then we use the linearity of the conditional expectation, right? And this is okay. Now we can use the tower property to go down to the local property here, right? So this is tower property. Which allows us to insert another conditional expectation of xm minus xm minus 1 given the information up to time m, then given the information up to time s. Well, but this is now by assumption 0. So we're adding here just zeros, and here we are. That's the proof. Okay. Okay, sorry. Are there serious questions? Okay. Okay, in order to state the Doob's decomposition, which I actually heading to, right? And this is chapter 2.4. I need another definition, which is the definition of predictable processes. Right. And so revision definition 2.33. Stochastic process. Let's call it H. Is called predictable if HT is ft minus 1 measurable for all t in T. And now, well, to keep it well defined, let us extend our filtration to the time -1, just to keep the notation shorter in the future, which is assumed to be the trivial sigma algebra. All right. I mean, let me not further comment on predictable processes, but I think in the end of the lecture and starting from next week, I think it will become very clear why this is actually a natural notion. Okay. Now the decomposition I was heading to. Theorem 2.34 is Doob's decomposition. And as I said, this I think provides you with a very nice situation behind what's the super and the sub-martingale. So if we start with the super martingale, but we will see later that the similar statement holds for sub-martingales as well. All right. So what I would like to consider is a super martingale. It's a super martingale. Then t is equal to a martingale m plus a predictable process, which is non-decreasing, and it's decreasing. This holds for all t and t, where we have two things. So first, we need to say what m is. So m is a martingale, and a is decreasing predictable process with starts at 0. Right, this is just a normalization we want to take. So what we see here is if we have a super martingale, which is a game which is not in favor for us, we can decompose it into a fair game plus a decreasing object. So decreasing process, right? So we can basically identify what is the part which is not in favor for us. And this is the process A here. Okay, and this decomposition is not arbitrary, it's actually unique. In this case, the decomposition, let's call it, stick to the same numbers as in the lecture notes, 2.4. 2.4 is unique. Of course, everything here, P almost surely. Okay. Other questions? Okay. Then let's come to the proof. Okay. So there are two statements we have to prove. The first one is, okay, we need to show that such a decomposition exists. And the second one is we need to ensure that it's actually a unique decomposition, or prove that it's a unique decomposition. So let's start with the existence part. All right. So okay, this is not, I mean, no. Okay. So what we want to do is, okay, we want to define or like find the process M and A. Well, so since at time 0, my process A is assumed to be 0, in order to have this decomposition, the process M at time 0 has to be equal to x0, right? This is the only way that this decomposition 2.4 can hold. And now we want to extend it, that M stays a martingale. And what we do is, I mean, keeping our local characterization in mind, we just prove, so we define MT, two definitions, as x0, right? And then we look at the process and we consider each round. And at each round, we make sure that this is a martingale. So in each round, we compensate here xn with so that it's a martingale, right? So we just subtract the conditional expectation of xn plus 1 given the information of fn for t. Okay. And now, okay, I mean, what you just said, I mean, let's check it, that this is really a martingale. So, indeed. T is a martingale. Okay. Well, as usual, so what do we need to check? Well, it's adapted. If you look at the martingale at time t, well, all these terms here, I mean, the highest order term in the sense of this has the highest index has exactly here this xt. So if you set m equal to t minus 1, you get an xt. So all the objects are measurable with respect to ft, and then the sum is in particular also measurable with respect to ft. So adaptiveness is not a problem. And well, since you have a finite sum of integrable random variables, also the sum is integrable. So integrability is also not a problem. Okay. So we only need to check the Martingale property. So we consider now m at time t plus 1, given the information of fmt. So we want to calculate that this is equal to mt. So let's plug in the definition and use the linearity of the conditional expectation. Okay, so that's minus xt plus 1. Okay, and now we have still the filtration ft. So right, this is, we just need to use the linearity of the conditional expectation with respect to ft and the definition like then, right? And now let's split the sum to the sum up to time t and minus 1, because they are all ft measurable, so we can pull them out. So that's t plus 1 minus xt t. Right, so this is your, oh, that was not the point. And now we have the term left, which is the last summand. So that's xt plus 1 minus ft, the conditional expectation of 1. Okay. Let me use another line. Okay, so this is just now the last summand. So that's xt plus 1 minus the conditional expectation of xt plus 1 given ft, given ft. Well, that's good, because this here, okay, make another color. So that's nothing else than. So this here is ft measurable, so we can pull it out. So what we get here is ft plus 1 given ft minus xt plus 1 minus ft, right? Because of the measurability, and this is 0. So we can come back to our blue calculation and see that this is nothing else than mt. And now we use the lemma which we just had before. So T is Martingale by lemma. So let's check the number. So this is the lemma we proved at the beginning of this section. So 2.32. So we have here 2.32. All right. Yeah. All right. And now we want to ensure that this decomposition holds. So right. So we have found a martingale, which is, well, looks nice, but and is really related. So it's basically turning each round of this process X to a martingale. But now we want to ensure that this decomposition here, which is as the orange box, is true for every time t. Okay. So what we need to do at time 1, obviously, to ensure that this decomposition holds true, we need to set a to be 0. This is actually what we claimed in the theory. And we want to define now the process A to be x t minus mt. I mean, this is the brute force idea to ensure that our decomposition 2 points, so the Doob's decomposition given by 2.4 holds true for every t. Okay, but if we do so, we need to check that this is indeed a predictable process and non-decreasing, and decreasing process. All right, okay. So now let's try to understand this process A. So what is A? A is k x minus m. And well, let's plug in the definition of m. So that's the sum from 0 to t minus 1. And now yeah, so this is definition. Right. So isn't this correct? Yes. Let me, right, that's here. Let me mark it. So, and so here's the definition of m, and that's what we plugged in here. Okay. And now what we see here is well, we can look at this summand here and just shift it. Right? So this is nothing else than, oh, wait, oh, sorry, here's something wrong. So we pull this in, and here's a plus. Right. Yeah, because we swapped here the order. Sorry. That's the same as shifting this term here, so the numbering. So that's xt, the conditional expectation of xn plus 1 given fn minus xn. Right? So this is, we pull this in and we delete this xt, the last term. For t being the index set without 0. Okay, and now let's look at this process. Well, first is we observe that the process is predictable. Right. How do you see it? So is predictable. Right. Let me take green again. So what we see this here is fn measurable. That's it, of course, if fn measurable, and we stop the sum by n minus 1. So this means the biggest one here is ftn measurable, and this is ftn measurable. All right, and this was the first property. Second one is obviously by the definition, we have that it's 0 at 0, and it's decreasing. Since if we look at each of the summands here, so if we this minus this minus xn is less or equal than 0, well, because x is a super martingale. Is a super martingale. To be more precise, we used again our local property, also a lemma describing the local behavior of martingales. So that's 2.32. Okay. Other questions? So indeed, so we constructed two processes M and A, where M is a martingale and X is a decreasing predictable processing starting at 0. Okay, and now we want to ensure that this is unique as well. I mean, that the decomposition is unique. So that's the second step we need to do, is to check uniqueness. Okay. Okay, if you want to check uniqueness, well, the standard approach to it is to assume we have two process or two decompositions, right? So let's assume there are two decompositions. Let's call them M and A. So this is the first one. And star is the second decomposition. And A star Buying 2 point. So they're both to assume that the sum of M and A and the sum of M star and A star are equal to X. Right? So this means M plus A is equal to X is equal to M star plus A star times T. Yeah. Okay. Well, this means if I look now at the increment of M star, for example, from T to T plus 1, right? So if I look at this, so what is this? Well, this is a predictable process. Well, that's obviously the same as M star T plus 1 minus M star T. And they're predictable, so they're both measurable with respect to Ft. So I can take the conditional expectation without changing anything. I can try a new color. Where is? Okay, that's not a good idea. Sorry, let's take this one. Okay. But now I can add the martingale here. The martingale M star times T plus 1. So he has to be a plus. And then I have to subtract it. So I subtract it. And what you see here, I mean, since I have the conditional expectation around is this M star T plus 1 is equal to, I mean, if I take the conditional expectation with respect to Ft, it's equal to M star at time T. So this is, I'm added a 0. And now I use here our decomposition. Let's call this star here. Let's call it dagger. What I can know that this is nothing else than if I leave away the stars, and well, now I make the same trick but in a reverse order, so I get that this is nothing else than A at time T plus 1 minus AT, right? So now, as I know that by assumption, A at time 0 and A star at time 0 are both 0, and the increments are the same, so we get that A is equal to A star for all T in the index set. And well, A is the same, and if I look now at dagger, then I also get that M equal to M star for all T. Okay. All right. Okay. So this is the uniqueness part. And as usual, I mean, please feel free to ask questions in the chat. So now let me also formulate the same theorem here for Doob's decomposition for submartingales as well. So let's take 2 point corollary, because now if we have proven it for super martingales, we can easily derive it for sub martingales as well. Okay, so let's so if XTT is sub-martingale, then we can again decompose it into a martingale and now increasing process A. Where? Right. Before, M here denotes a martingale. Is martingale. And AT is an increasing, predictable process. With this assumed to be, I mean, this is also just a convention. So we assume that at time 0, it's 0. And in this case, this decomposition, no, this composition here is so if I have a sub-martingale, I get a similar decomposition with an increasing process, right? So you see sub-martingale, which is a game in favor of you. You see if this models, for example, your game process, well, you have a martingale, which is means the probability, I mean, the expected value of your gains and loss are 0, but then you have an increasing process, which ensures that you also really make gains. All right. Oh. The decomposition 2.5 is unique. P almost surely. Okay. Proof. Oh. Let me show it. So, I mean, now we don't need to redo. I mean, you could do the same proof if we have done for the super martingale case and just see, I mean, how it changes if you have now a sub martingale instead of a super martingale X. But there's a easier trick here to do so. So what we want to do, so we call, and this is lemma, which we proved today, 2.29 means X T here is a sub-martingale if and only if X minus T is a super martingale. Right? And well, so what you doesn't tell us, so we apply Doob's decomposition to the X minus, right? So for super martingales, so that's theorem 239 to the super martingale X minus. And then lemma, the one we want to prove here. So check our corollary. The corollary just follows. Right? And if you see, I mean, if you have a martingale, so if you have here m minus, so the minus of a martingale is again a martingale. This was the linearity. So martingales are a form of vector space. And well, the predictability is not changed if you have a martingale. Right, so here the predictable part is not changed. A is still, so a minus 0, at time 0 is still 0. So the only thing is swapping is we swap increasing process to a decreasing process, or a decreasing process. So the only thing where you need to be careful is by doing so is that here the decreasing process from a submartingale is swapped to an increasing process in the case of a supermartingale. Okay, so that, oh, all right. Okay. Okay. And let me come to the final section for at least for this part where we talk about martingales. And these are discrete stochastic integrals. Okay. So what we do again here is, right. So here it's again, I mean, yes. So if you, of course, these Doob, I mean, it's not, of course, but I mean, what you can show is that these Doob's decomposition holds for much more general index set than our index set T. But here again, if we want to talk about integrals, we want to ensure that we're in a discrete time setting. Right? I mean, I said already that we do it now for the whole course. But here, I think it's really crucial that we have discrete time setting, because if you think about continuous time, integration theory gets much harder. And then it's, yeah, it's a new course. And well, the first thing we want to do, the second thing is just to assume. So we always assume that here was that process K, so process X is an adapted real valued stochastic process is assumed to be integral. For every time. Right. Okay. So I think here in this setting, it makes in particular sense to keep an example in mind, because this is how we use the stochastic integral most of the time. So I think example is to say, well, X is equal to the price process in the binomial model. Right. Because now, well, we want to, I mean, at some point we want to invest. I mean, from next week on, we want to invest in this price process, right? So, and the integral, as we see in a minute, I mean, models exactly the gain or loss process we have from taking positions or investing into a financial market. Let me define what I mean by discrete integral. So that's definition 2.36. Okay, I mean, if we want to talk about integrals, we also need to have an integrand. So let h be a predictable process. So the predictable processes are our integrands. And then the discrete stochastic integral of h with respect to x is the stochastic process we denote this by h dot x. Right, this is in %, given by sorry. So let me, so h dot x is defined as the sum of starting from 1 up to time t, where you multiply h at time m with the increment of x. So of x. For t and t, and we make the convention that the integral process of h with respect to x at time 0 is just set to be 0, right? Because I mean, this sum is here not well defined if you take t equal to 0, so we just set the integral process to 0. Right, okay. So that's our discrete stochastic integral. And well, it should remind you on the classical Riemann sums you have seen in analysis. And now let me give you a bit the financial situation behind this. So what? So, financial text. So right. So if you think about your price process as, and well, H to be your trading strategy, what you have here is following. So H stands for the position of a trader in the T trading period. Right, so if you look at this, I mean, this usual picture we have, so you start at time 0. Right, so this is your time horizon. Then you have here time 1, and let's say time 2, and well, wherever it stops. So you have your price, for example, which is S0, and S1, S2. So you take a position which is labeled by 1. So at time 0, you take the position H1. And here you see why it makes sense that it's predictable, right? So it has to be measurable. So H1 has to be measurable with the information given by the price is generated at time 0. So it has to be measurable with respect to F0. And then the price is evolving. So if you have then, what's another color? Yeah. So if you have your position and you multiply it with 0, and then this here is evolving, the gains and losses you make is given by S1 minus S0, right? And this is at this point. And if you keep trading like this, so what you end up with your gain process is, well, up to time t, you have always your position, and then the price is evolving. And in each period, it's going up or down. And this is the change in the mth period. Right? And this is then, where's my, what we define as h dot s at time t. Right? And here you see why the notion of predictable process is rather simple. It's just a way to bookkeep your trading strategies. And we do it like the position H1 denotes the trading, the position in the ith trading period. And this means it has to be Fi minus 1 measurable. And you see, I mean, the gain process from trading in the market is here just given by the discrete stochastic integral. Okay. Let me conclude with one theorem regarding stochastic integrals here. So that's theorem. So the last thing we do for today, it's 2.37. Which, as we expect, so let's let me make it recall it. So we have a process which is assumed to be an adapted real valued stochastic process when it's assumed to be integrable. And then we have two claims. The first one is that this process X is a martingale if and only if for any predictable process H, the stochastic integral of H with respect to X as a process in time is a martingale. Okay. So again, in financial terms, this means, well, if the underlying price process is a martingale, then also our capital gain process is a martingale, right? So if we gamble the market, this is again a fair game. This is if and only if the market is a fair game. And then we have the analog statement for super and sub martingales. So X is a sub super martingale. Again, if and only if for any predictable process. So that's of course a process. With it's non-negative. Right? Otherwise, we could swap signs, and this is not good in the if we have super and sub martingales. The stochastic integral here, so h with respect to x time is sub super martingale. Right. So this is here rather crucial. So here you have to be careful. We need to have non-negative integrants, otherwise we might swap the integral sign, and this would destroy the super or sub martingale property, or just change it. All right, we finish briefly with the proof. So, so one direction. Okay, let me just check the Martingale property. I think the rest is clear again. So we get, if we take the conditional expectation of the integral of h with respect to x at time t, conditional to the time t minus 1, well, you do the opposite thing. You decompose it into the steps up to time t minus 1 plus here the thing which is not measurable. So we have here the last summand. And well, that's good. So that's what you have to, it's not x, it's x. Right, this is this, and then now you can, so this is integrable, so you can pull it out here. So you have h, and then you have the, well, this is now martingale here, so you see what I'm writing is just 0. So that's by the Martingale property. Oh, yes, minus one missing, it's just 0. Right, so you have xt. So that's a martingale. Is martingale. And now the other direction goes as quickly as the first one. So what you do is, well, let's take a t0 in our index set t, and we consider the indicator function. So we take the integrand to be the indicator function of t being equal to t0, or I can write probably this in a more standard way, right? Wait, and now what we get is, or if we consider this trading strategy, we have always 0 for t being less or equal than t0 minus 1. So what we get is 0 is equal to, because this is by the assumption of Martingale. So this is t0 times tf minus 1. This is by the definition for trading strategy, nothing else than x at time t0 given f at time t minus 1. Right, this is measurable, so we could pull it out. And this means t is Martingale, again by our lemma telling us that it's enough to check the local properties here. Right. All right, and now, well, the other claim works similar, so it's good practice for you to check this yourself. All right. Are there questions? What do we mean by position of a trader? Sorry. Thank you. The position, I mean, we will start with the more financial part again from next Tuesday on. So what it means is this H here denotes the number of shares you hold in the asset S, right? And this is the position you have in the market. So here, if H1 is, for example, 3, this means you have 3 risky shares with that the price as 0. All right. Then I wish you a nice day, and we'll see you next Tuesday. Bye.